Now we learned what is a linear combination. You take these basis vectors and you can create all the other vectors of them. So first thing that you need to learn about these vectors is if they are orthogonal, for example, to each other, it's not necessary, but if they are orthogonal to each other, like I, J, and K, for example, you cannot use I and J to represent K, which is in the other in Z dimension. You simply cannot. They are useless for that. So these vectors are called linearly independent vectors, and the idea of them is that you can describe other vectors with these vectors, but you cannot describe K, for example, with I and J. And then you have a different concept which is called linearly dependent vectors, and these are the vectors which can be described by combining the other two. So the question for you is, if you have these three vectors, I and J, which are normal basis vectors, and we have some vector P, which is in the same plane, is it necessary to have these three vectors to define the two-dimensional space, or is one of them not necessary, or one of them is redundant? If yes, tell me which one is redundant, which one is not necessary to describe the space. And would someone like to try? If not, I can tell you. For example, P is not necessary, because you can use I and J. You multiply I with some negative number and J with some negative number, and you create P. But then you might think that space is something which always looks like this. You might think that space is some kind of structure which can be recreated by using grids. Yeah. For example, then this is X. Oops. This is X. And this is Y, and space is somehow some kind of a grid, yeah? But this is not really necessary. We can have axis, which X is like this, and Y is like this. So the space does not need really to be, and then what can happen is that some kind of, we can have that, for example, 1 and 2 are in this direction like this. And in the other direction, it could be that they are much further apart, like this. So the grid lines also do not have to be, in this space, do not have to be equally, they need to be distributed equally, but their length might vary. So the space can have different configuration. And this is what I want to show you here. I can use I and J to describe P. So then I and J are linearly independent, and then P is linearly dependent. But I can do the other thing. So this is what I did. I multiply I by negative 0.88 and J by negative 0.47, and I represent P. But I can also use I and P to represent a space, and in this space we can use I and P to represent J. You see, it doesn't matter which one I take out. You can now use I and P to represent J, or you can use P and J to represent I. And if you have two vectors, for example, now P and J, everything that you can reach with these two vectors is called the span of these vectors, yeah? And you have if you have two-dimensional space, then two vectors will span the full space, unless they are parallel to each other. If you have two vectors in 2D that lie on the same line, so this is the line, and you have one here, and you have one here, these two vectors are linearly dependent. Why? Because I can use this line, put it here, multiplied by some number, and create this vector. Or I can create this vector, put it back here, and then stretch it a little bit, and I get this one. So with these two vectors, although they are two vectors, I can reach only the same thing that I can reach with a single vector. But if they are not parallel, if one is just a little bit in different direction, then with these two, I again can reach anything into this space. Yeah, and this is the illustration of that. I have here U and V, some vectors which are non-orthogonal. I multiply them with some number A and B, and then their addition can reach any point. So the tip of this green vector can reach any point into this space. And then the same happens in higher dimensions. If you have three vectors in higher dimensions, which are linearly dependent, which means I cannot use one vector I cannot use two vectors to describe the third one, just like I showed you on the image. Then they've spanned the full space. But here, what I have here is I have three vectors. We have green and yellow one. You see it's there. And you have the purple one. And the purple one is a linear combination of the green one and the yellow one, because it's addition. So it's the purple is yellow plus green. Therefore, these three vectors, we have three vectors, but they're linearly dependent on each other. Only two vectors are unique in this space. And you can see, when this happens, they cannot reach any point in 3D space. They can only reach a plane in 3D space. So their span is less than full space. If they were linearly independent, they would span the whole space. They would reach any point. But right now, because they're linearly dependent, they reach only a plane in this space. And then imagine now that yellow and green one were parallel to each other. And then their addition, the third one will also be parallel. If you have three parallel vectors, in three-dimensional parallel vectors, they will make a line in space. So they will be even more restricted what they can show. So this is the idea that you need to keep in mind. And now we go into a little bit more abstract things. I will now open a new notebook. If you just want to follow, you do the same as before. You go to this website. Yeah, you enter this URL. Oops. What is the problem? It worked just before. You just take this link. Oh no, this is you need to go to GitHub. You go to this link. This is my name. You find this machine intelligence. You again go to Google Colab. You find GitHub, which is where my code is. You paste the link, and then Google browses, finds the notebooks, and then you find Introduction to Matrices, and then you can run the code and whatever. If you want to do it on your own, sometimes. But I will not do it. I will follow from my notes. So, let's continue. Now let's see what matrix is about. So we define vectors are this kind of vertical arrangement of numbers in square brackets. And matrix, when you see it at first, it looks different but similar. So what we have here is the matrix is a kind of rectangular arrangement of numbers. It's just numbers put in a kind of a table. It looks almost like an Excel table. You have rows and columns. These are rows. These are columns. And then there are certain numbers in each combination of row and a column. And usually we describe vectors with a small letter and arrow above it. And usually we represent matrices with capital letters. And then if we want to talk about a matrix, we need to define, we need to kind of say what is its size, how to speak about it, what is its shape. And the size of a matrix is defined by first saying how many rows it has, and then how many columns. For example, this one has 3 rows and 4 columns. So we describe it as M3-4. So 3 rows, 4 column matrix. If you multiply 3 and 4, you get 12, which is the number of elements in a matrix. Now, why we have matrices? You know, why did people describe a movie? Why is a movie called Matrix? Why matrices has something to do with this idea of cyberspace and whatever, you know, this cultural thing that we kind of, when you think about the matrix, it's something weird. But there is really a single precise meaning about what matrices are about, because they are just a structure of numbers. And in the same way we can use numbers, as I told you, to do many things, to count, to measure, to describe certain properties. We can use vectors to do many things as well. to describe a force, but to describe motion and all of these things. Also, we can use matrices for many things. We can use them, for example, to solve systems of linear equations or to transform space. But there's no one single meaning about matrices. They are simply a structure of numbers. And you can see that this structure can be very useful in certain contexts. But in linear algebra, matrices do get some meaning in terms of what they do to the space and to vectors. And the main thing is they describe something called a linear transformation. So we so far used vectors to show movement in space, for example, or a force. So something which requires us to have a direction and intensity. Matrices transform the space itself. So you can now imagine the movie. What was the movie when there was an architect who is kind of Inception? So if you've seen the movie Inception, then you can see that the space itself starts to transform, starts to bend and stuff like this. Well, matrices does not allow it to bend it in this kind of very smooth way, like you've seen in Inception, but do definitely transform the space. They make the structure of the space different. For example, what matrix can do, it can rotate the space 90 degrees or any angle. Or it can stretch it in one dimension, or it can squeeze it in one dimension, or it can rotate and then squeeze it. It can squeeze only one axis and the other one stays the same. It can do many things to the space, and these are called linear transformations. And what is, for example, a property of linear transformation? Here you see an effect of a very simple linear transformation. I did not change the space much so that you can recognize what happens. So this is the space that we are used to, and this is the space which is a little bit transformed. You can see the figures look different. To explain you simply what a linear transformation is about, you can imagine that space itself is empty. It's like it doesn't really have any visible structure. It has a structure which is defined by these vectors I and j, but it doesn't have visible structure. What we can do, we can use some helper devices. For example, you can use coordinate axes to define the principal directions of space. Or you can use grid, like I used here, blue and red lines, which are parallel to the grid lines, and then this shows some kind of spacing in this space, some kind of metrics. If we have something which is a linear transformation, what needs to happen is that origin of space in the original space and in the transformed space needs to remain the same. You see, they're both centered at 0, 0. So however you transform the space, 0 needs to be the center of the space again. This cannot move. And another thing that needs to happen is that these grid lines, they need to remain parallel to each other and equally spaced. So if grid lines start stretching one from the other, this is not a linear transformation, it's a non-linear. Or if grid lines start changing direction, like it happens in the movie, this is a non-linear transformation. So linear transformations are a little bit simpler transformations. And this here on this animation, you can see that we start with two normal vectors I and j. Actually, they don't even have to be starting from our typical orthogonal configuration. They start somewhere and they end up somewhere. And you can imagine now, as these red and blue lines, which define the space, rotate and move, the whole space goes with them, yeah? But there's no way for you to describe it, so you can just imagine that the whole space now turns and extends. Okay, and the nice thing about these linear transformations and matrices is that if you want to mark what happens to the space, if you want to mark a rotation or any kind of transformation of this space, you can use it by using matrices. And the procedure to do this involves only following what these two basis vectors do. Or if it's a three-dimensional space, 3 basis vectors. Or if it's a 100-dimensional space, 100 basis vectors. But the nice thing is that you only need to keep track of them, where they land, and then you need to capture where they land in terms of coordinates and put these coordinates in a matrix. And that's it. That's enough to describe the transformation of space fully. And this is very nice, because imagine, if I am able just to capture where these two vectors land, I can then take any figure in this space, in the original space, and I will know where will this figure land in the new space. So if I have for example, I don't want to open Photoshop now, but if I'm in Photoshop and this is my canvas and then I have a picture here and there's something in this picture. And then if I say transform and then I get these 4 elements here to transform this picture, and if I push these things, for example, push this line, my picture becomes this. And everything in it gets transformed. And this is what matrices do. You just keep track of where I and j lands. In this case, I and j would be these guys. It will be this guy and this guy. You just keep track where they end up. So this one ends up here, and this one ends up here. And only by that you can transform all the other elements in this space. And this is very nice, a very powerful idea. And this is why matrices are using computer graphics. They rotate the cameras, they rotate the space, they rotate the elements. They not only rotate scale elements or flip them or whatever you want. I will now show you how this works. It's really nice. So our goal is, this is our starting space, this is our end space. I don't know if this, can you see these numbers or should I make it larger? Can you see the numbers? Starting space, ending space. Okay, what I did, I somehow transformed the space. And then what I told you, what matrices do, they capture where the basis vectors land. So I used to be 1, 0, j used to be 0, 1, but now after the transformation, in terms of the old space, I lands on -1, 3, so -1, 3, and j lands on -2, -1, so -2, -1. And you just put this first vector as a column of this matrix, and you put the second vector as a column of the matrix, and these 4 numbers, in this order, are enough to describe the whole transformation of space. So this matrix, if you know how to compute with it, can be used to tell you where all the other elements go. And this is super powerful, and I want to show you how does that work. I will introduce you the procedure later, but this is the important thing. You name it M, you say what numbers are there, -1, 3, -2, -1, and you put it in your pocket, and it's there for you. You know how to transform space from this configuration to this configuration, just with these 4 numbers. And now let me show you some common transformations. For example, if I want to rotate the space 90 degrees clockwise in this direction, yeah, you see what I do. I just put I 90 degrees here, j 90 degrees here, and I capture the coordinates of I, which is 0, -1, the coordinates of j, which is 1, 0, put it here, and now I have a matrix which does the rotation, 90 degrees clockwise. Then I find another transformation, 90 degrees counterclockwise, and I get some 4 other numbers, and I just call them M rotate 90 minus. You see, now I'm just putting in my pocket different matrices. They don't need to change, they remain the same for the 2D space. If in 3D space they would need to be larger, because they will need to capture 3D vectors, which means there will be 3 vectors of the length 3, which means that the matrix will be 3 columns and 3 rows. Okay, then these things that I show you with Photoshop, this thing here, this is called a shear transform, and what it does is I remains the same, but j goes here, so then I remains 1, 0, but j becomes 1, 1, because it comes 1 to the right, 1 up. And then I have another matrix, another transformation of space captured here. And now I have few elements. Now let's see what we can do with them. For example, this is shear, M rotate 90 minus, M rotate 90 plus, and this M. So we have these 4, and now we're going to just play with these matrices. There is one more matrix, which is a little bit funny, because it doesn't really do anything. It is a matrix which doesn't end up doing anything to the space. So where you start is where you end. But this matrix is also very, very useful, especially for solving systems of equations, because I remains where it is, 1, 0, and j remains where it is, which is 0, 1, and this is the matrix of the size 2, and this is the matrix of the size 3. An interesting pattern to observe here is that the ones are on the diagonal and all the rest of the elements are zeros. So this is how this identity matrix looks like. Okay. Now, the most important thing about matrices here is how, if we know where the space, how the space gets transformed, how then we translate a vector from the old space, some arbitrary vector or some point in space, to a new point in space after the transformation. How do we do that with matrices? And we already said the transformation that we are interested in is captured by these. Actually, these four numbers are wrong. We should look at these four numbers. This is a mistake I made. It should be -1, -2, 3, and 1. Okay, I will remove it so that you don't see it. I can now describe what's going on. So we have I, we have J, so this is the original space. You see the grid. And then we have P, this is a new vector. Its coordinates are -0.5 in x direction, in I direction, let's say, and -1.5 in j direction. So we can describe it as a linear combination of our basis vectors I and j, like this. -0.5 I, -1.5 j. Okay, these are the coordinates. Now we do transform the space. We rotate it and we extend it. So I now gets longer than j. They're not longer equal, and they are rotated in a funny way. This is not even 90 degrees anymore. What we do is we capture where does I land, it is -1 and 3. Where does j land, it is -2 and 1. And this matrix is now used to transform P. This is the next step. This is the P. And this is the new P. This is where P lands in the new space. And I want to show you how did I find where the P would land in the new space. So bear with me. What I did is I took the old coordinates of P, so -0.5 and -1.5, and with the first one, I multiplied our first vector, so I multiplied these coordinates, so -0.5 times the first vector, -1.5, which is this one here, by the second vector, which is this one. When I add them, so this is 0.5, this is 3 times -0.5 is half of that, negative, so -1.5, this is 3, and this is 3.5, sorry, this is a mistake. Oh no, this is -0.5, this is -3, this is +3, sorry, again a mistake, +3 and +0.5, you add 3, +3.5. Sorry for the mistake. And then you get that in the old space, the vector P will come to the coordinates 3.5 and 0, which is here. So 1, 2, 3.5, 0. So P will go from here in the new space to here. Yeah, this is what will happen. But now bear in mind what happens. With these I and j, I have one coordinate system. This is this coordinate system. With this I and j, I have a different coordinate system, which is here. You see, it looks a little bit different. And the interesting thing to ask, how does these coordinates, -0.5, what happens to them when we transform the space? And the super interesting thing is that they remain the same. If we take this P in the old space, which is 3.5 and 0, and look at it only in the new space, now we here on this image number 4, we completely remove the old space, only remain with the new things. You can see that the coordinates in the new space are still the same coordinates. It's still -0.5 and -1.5. You see, I just take I multiplied by -0.5, I get here. I take j multiplied by -1.5, I get here, or here, depends, they're the same, and then I get the negative P. So as you can see, the parameterization of the vector remains the same. The coordinates which you use to describe the old vector remains the same. The only thing that changes is the basis vectors themselves. This is why they are so crucial. You just need to remember where these two guys land in terms of the old space, and that's it. And this is the procedure here, how I actually computed this. You can see it here. What this involves is to multiply this vector by a matrix. So you put a matrix before it, and multiplied, and then this matrix transformed the vector. So the vector P was, as I said, negative 0.5, negative 1.5, so this one here. You can see it here. I multiplied by this matrix N that we drew. I multiply this number with the first column, this number with the second column, I add them, and I get where does P land in terms of the new space, in terms of the old space. Yeah. This is not still a real matrix multiplication, but we will get there. So this is just kind of slowly introducing it there. And now, the most interesting thing about this whole matrices comes with a question: can we combine operations? Can we, for example, rotate the space 90 degrees? Then can we stretch the y coordinate 2 times? Then can we stretch the x coordinates to the right? And then can we rotate it for 72 degrees on the other direction? Can we combine these operations? And then the answer is yes, you can. Of course you can, because you can just do these operations one after another. But one more interesting thing is that if you have multiple matrices representing multiple operations, if you just multiply these matrices with each other, for example, you have 4 transformations in 4 matrices. If you multiply these 4 matrices, you get a single matrix which combines all 4 transformations in one. So you can take 100 transformation matrices, which do 100 different things. You multiply them together. You get one unique matrix of the same size as these matrices, which does all of this at the same time. And this is really incredible, because you can use then one matrix which does a result of 10 matrices. And I want to show you how this works. So we had a vector Q, remember the vector that we transformed. And then if you want to first rotate it by 90 degrees counterclockwise, and then do the shear transform, do the Photoshop thing, yeah? If you want to do that, what we can do is we take the old vector, we multiply it by our rotate 90 degrees matrix, which we defined above, and then we get a matrix which we called Q rotated. So this is now Q, which is rotated 90 degrees. Then the next thing we do is we take Q rotated and multiply it by a new matrix, which is M shear. So this is the one which squishes it toward the right. And then you get the final matrix Q final. So that's one way of doing that. You can imagine this is not very complicated. You just do the same operation twice. But the interesting thing is, if we want to rotate and shear at the same time, we just multiply the shear matrix, so the one that comes at the end. So the last rotation goes to the left, and the rotation before it goes on its right. So first we do rotate 90 degrees, then we do shear. We multiply these 2 matrices, as you can see here. This is the result of the multiplication. I didn't tell you yet how to do this. Funny thing is that this new matrix, we can now call it rotate and shear matrix. This will be a matrix that does both at the same time. And now I want to show you, I now want to show you an example. So look at this animation here. First, I rotate with this matrix here. Then I shear with this matrix here, and my vector ends up here. But if I multiply them and get this matrix here, I'm doing these both things at the same time. As you can see, I'm combining multiple operations with a single matrix, which is this one. So I can either compose operations one after another, or I can multiply the matrices and get it at the same time, which is quite nice. So you can see matrix multiplication, although it's just a formal operation of doing something to 2 groups of numbers, has certain meaning which is very useful in linear algebra. Actually, it makes linear algebra itself useful, because without this, it's much more complicated to think about operations. But with this, then matrix multiplication, what it does, it allows you to compose different transformations of space. And this is why it is great. This is why it is useful to learn what is matrix multiplication about. Finally, I want to show you how matrix multiplication works. And it's the most boring part, but simply it's very useful to know what's going on. Although at the end you will use computers to compute matrix multiplication if you ever do it in your life. And I think you will, because you're young and your careers will involve more computers than you imagine. And Yeah, let's just take two matrices and define how to compute their product, because it's not so straightforward. The computation itself is simple and boring, but at least what you can learn is when you can multiply them and when you cannot, because that's the most important part. The most important part is to decide if you have matrices A and B, can they even be multiplied together? And the second thing is, if they can be multiplied together, what will be the size of the new matrix, which is a product of these two? And this is what I want to show you today, and the multiplication itself, we're not going to do that. I'll just give you an animation to show you how does that work. Okay, A is a matrix which has three rows and 4 columns, so it's a 3 times 4 matrix. And B is a matrix which has 4 rows and 2 columns. Yeah? So in order to compute them, they need to be compatible in size. And here it says, so this is the rule. Of course, you're not going to remember the rule. I will show you how it really works. To compute the matrix product A times B, the number of columns of matrix A needs to match the number of rows of columns B. If this criterion is met, then the product matrix will have the same number of rows as the matrix A and the same number of columns as the matrix B. So now let me show you what I'm talking about. So A is, what was it? 3 times 4 matrix. Yeah. So A is 3 times 4. And we are multiplying with B, which was, I think, 4 times 2. So you can think of it. So this is the number of columns. This is the number of columns. So this is the number of rows. So 3 rows. This is what I said at the beginning. This is the number of rows. This is the number of columns. This is the number of rows. This is the number of columns. So what I said is, as a rule, the number of columns of A needs to match the number of rows at B. And these are just these two numbers. So this is the number of columns of A, and this is the number of rows at B. Yeah? Simple. If these are the same number, you can multiply them. And you can see that they are. So it works. First step done. They can be multiplied. Funny thing is, can we multiply B and A? Because B now has 2 columns and A has 3 rows. So funny thing is, I can multiply A and B, but I cannot multiply B and A. This would not be allowed. But now let's see, let's examine further A times B. If this is working like it is now, then the new matrix will have the number of rows of the A and will have the number of columns of the B. Which means if you have, let's say that this is equal to C, yeah? So then the C will be of the size 3 times 2. Okay, so C will have 3 rows and 2 columns. Simple, no? So this is what you need to know exactly. And now the other part you need to know as well, but there's nothing much to know. It's just combining rows of one with the columns of the other. So now let me show you what else you need to know. Now that we defined, okay, this is possible, a new matrix will be of the size 3 times 2, then we actually can put these elements on paper and say, okay, these are these 6 elements. And now how do we actually compute the matrix elements? And this is what you see here. To compute this element here, which is in the 2nd row and 1st column, you just take the first matrix, takes its 2nd row, which is these 2, 2nd row, and 1st column, which is this row. So if you put them in this geometrical way, you can see that this element is this whole row dot product with this whole column. This is what you have here. Dot product simply means A21 times B11 plus A22 times B21 plus A23 times B31 plus A24 times B41. So these are these four operations. You add them together, you get a single number, and you put this single number here. Simple, no? It's just boring. I admit, it's very boring. To get this element, C32, you do a dot product of the third row of the matrix A and the second column of the matrix B. You put them here, and you just multiply A31 times B12 plus A32 times B22 plus A33 times B32 plus A34 plus B42. It's here. Okay. Now I have an animation for you, simply showing you what's going on. What are you multiplying? Yeah? You just look at the animation and everything is kind of clear. It's just a mechanics. You can see it's a mechanics. You can see a robot could be doing this for you, yeah? And then you realize, yeah, of course, this is actually how computers work. They do these things very well. You should use a computer to compute this. Because why? If not, then you need to compute this by yourself. It's how you do it. So you can either use a computer or do it yourself. Even it's not that difficult to do it yourself. It's just incredibly tedious and stupid task to do. Then there is also matrix addition and subtraction, but unfortunately addition and subtraction do not have a very clear geometrical intuition to tell you that now A plus B does something special in space, because it doesn't really. You can check it for yourself. It cannot be really generalized what it does, but what it does is you simply, if you have matrix A and B, they need to be of the same size. If they're of the same size, then you can add these respective elements. So you add A11 to B11, you add A12 to B12. The same with subtraction. It's very easy. You just subtract B11 from A11, subtract B12 from A12. Multiplying by scalar, this can have some meaning, but I will leave that to you if you're ever interested. What does this do to a vector? If you multiply it, it has to do with scaling, of course, with scaling the transformation itself. But I don't want to go there. I want to show you what the operation is. Operation is, if you want to multiply by a number, you simply multiply each member by a number. And now I want to show you how does this work in code before we finish. It's very simple. I again import this NumPy, which is the library of working with matrices and vectors and tensors in Python. And now I want to create these vectors, these four. You see, I do it, I mean, I cannot describe in words how do I do it. You can see it on the image. You just make some rows and some columns, you put some brackets in a certain way, and then you put these numbers in. So I can encode A, I can encode B, C, and D. And now you have them. Now you can work with them. Now I can say, okay, print A, just to make sure that I didn't make a mistake, and then computer prints out this thing. You can see it's the same numbers, so it works. I'll print B, just to make sure I didn't make a mistake, C and D. Okay. Now I say, what is A plus B? And I ask a computer, and computer crashes. It says operands could not be broadcast together with shapes 3, 4, 4, 2. So computer is a little bit cryptic, but what this really means, this error, is that I'm trying to add matrices which have different shape. So this one has 3 rows and 4 columns, this one has 4 rows and 2 columns, so they're simply incompatible. You do not know how to add the elements because they do not have the same elements. One has more rows, one has more columns. So you cannot do it. But I can add C plus D. So what this does is add 1 to 2, 3 plus 1, negative 1 plus 3, negative 1 plus 2, and then it gives you this matrix here. And I can always add a matrix to itself because they have the same number of elements. Yeah? I can also subtract a matrix from itself and get all zeros, which is not a very special thing to do. But I can also multiply it by a number. For example, I multiply A by 5 and then you get this, or I multiply by 25, I get this. Nothing special, or negative 5. And now let's do the matrix multiplication. For that we use an operator called dot, and we say what is A times B. Question is, can they be multiplied? If it works, they can, but it's also simple to test it. This one has 4 columns, this one has 4 rows. It works, yeah? puff, puff, it works. This one at the end has 3 rows, which is 3. This one has 2 columns, 2, so the size will be 3 times 2. Yeah, 3 times 2, it works. But as I told you, I cannot do B, I cannot matrix multiply B with A, because they are incompatible sizes. But I can do B times C, I can do B times D, and if the matrices are the same size, or if they are square, for example C and D, then I can do both. I can do C and D, and I can do D and C, you see? If they are square matrices, which means they have the same number of columns and rows, then this is possible to do. Which just means some operations of space can be applied. So you can, in some operations, you can first rotate and then stretch, and then this is somehow the same as stretching and then rotating. But in some cases, some kind of transformations, this will not be possible. Because there are some transformations which also depend on the shape of the matrix. If matrix is a square matrix, which it has the same number of rows and columns, this means that this matrix, what it transforms, remains in the same space. But if the matrix has less columns or rows, then sometimes what happens is that then the matrix transforms the space in a way that it collapses one of the dimensions. For example, Z dimension gets squished, it doesn't exist anymore. And in these things, then you cannot really recover the original space. You lose some information. Therefore, you cannot combine operations and expect them to give you the same result if you combine first the first one and then the second one. Then it will not be the same as the second one and the first one, because you would be collapsing the space and losing information. And I guess that's it for today. Thank you for listening to this. I hope it was not too technical, but I think it can be useful for you if you ever stumble upon machine intelligence and then you want to do some tutorials, but you have really no idea what's going on there. So at least this will give you some insight in what's going on. Do you have some questions, maybe? Absolutely. If you use any CAD software or any modeling software, these transformations are basis of the operations that you do to the objects. For example, if you extend the object, if you make it higher, if you rotate, this is all implemented by using matrices. So all kinds of operations that you do on your computer, if they have to do with space, they are done by using matrices. And it's good to keep that in mind, to not just take tools for granted, but to understand some principles behind them. And if you would like to imagine some new tools, you can get also inspired by some math which can be used to accomplish that. So it's not used to design architecture, but it is, if you use software to design architecture, then you use actually these things, but you're not aware of doing that. Yeah? So that's the thing. If there are no more questions, then thank you so much for coming, and I think next week you will see Ludger again. Thank you.